Okay, so from yesterday, we know that you remember about eutectoid points. Okay, so when we have gamma austenite, and then we cool it down, it become alpha and ferrite, right? And we heat it up, it become austenite as well. So it is austenite. It's become ferrite and cementite. And this structure together is called eutectoid structure, and if you remember, all of them is called perlite. Okay, so this is at composition is around C of the gamma is 0.76% of carbon, and here the ferrite is when 0.022% carbon, and sorry, the Fe3C is 0. No, not 0 point, yeah. It is 6.7%. Okay, so here it's actually from the phase diagram. Maybe let's look at the phase diagram here. Maybe look at the phase diagram. Yeah, this one, yeah. Okay, remember from the phase diagram, you have the gamma austenite with the 0.76 weight% of carbon. When we cool it down, that becomes ferrite at 0.022 weight% of ferrite, and 6.7% of carbon in, which is the composition of carbon in cementite. Okay, so this one is the eutectoid reaction or eutectoid point. Okay, so I'm gonna go back to the PowerPoints. Okay, so if you look at from the time point of view, the equilibrium is actually taken place at quite long time. Okay, it's quite a long time. It takes some time, of course. Why? Because those molecules, those metals molecules need to rearrange themselves. They have to move. They have to have a diffusion and to make a ferrite and cementite. Okay, so just imagine you have you haven't been in OSKM ya, orientasi studi keluarga mahasiswa ya. When I was a student, and then I was the what's called panitia ya, like the leader of each group. So at that time there were about 3,000 students, the new students at ITB, and we gathered together in the hall or the park outside the Aula Barat, yeah, of the West Hall, and then we have to rearrange ourselves, for example, based on name or from student ID or based on the groups, for example. So it takes time. So when I see from just a little bit up there, and then I can see all the students try to rearrange themselves, it is quite slow or something. Okay, that's also maybe similar analogy with solid, because solids compared to liquid and gas is actually, it's more the diffusion is much slower compared to the liquids and also to the gas. Okay, so if you see from the time point of view, this one is actually quite long. Okay, however, we know the limit that when we cool down austenite, it becomes ferrite and cementite. So this is actually This is from the phase diagram. Okay, but from the kinetics point of view, or the if we include the constraint, the time is actually going to be quite long time. Okay, and in reality, usually we need to be fast. Yeah, we need to be fast. We need to have a good high throughput of the metals every day, every month, every year. So then we can't wait if we just wait until it goes to equilibrium. So that's why we're gonna see about the kinetics of that, which is called phase transformation. Okay, so here, so that's the introduction, which is actually similar. So, oh yeah, before that, we know that it happens at 0.76 weight% and at temperature of 727 degrees Celsius from the phase diagram. Okay. So now the physical properties of material depend on the microstructure. So if we process them in a fast way or like in a moderate way, it's actually the microstructure of the alloys also will be modified by a phase transformation. Okay, and then the development of microstructure in the single or two-phase alloy typically involves some phase transformation, which is the alteration in number or character of phases. Okay, so the process when they start to transform from one phase to another phase, okay, because of those equilibrium, is called phase transformation. Okay, and of course the the phase transformation needs time, and it is called a transformation rate. That's just a measure which is 1 over t 0.5, and then t 0.5 is the time to achieve 50% transformation. Okay, so let's again include I won't be I will always repeat this reaction because this reaction is very important. So if we have a gamma, and then if we cool it down, become alpha and cementite. Okay, and if we heat it up, become austenite again. So we have austenite would be transformed into perlite, and then perlite, if we cool down, will also transform into austenite. So the transformation from austenite and perlite, we can plot it in this diagram. Okay, so if we actually do the transformation at the equilibrium temperature, wait, I think I'll need to close the door. Okay. Okay, so if we do this at 727 degrees Celsius, it's gonna take a very long time. So let's see. So this is a transformation diagram. The horizontal axis is time in a second, but in a logarithmic scale. Okay, so this is 1, and then this is 10 to the 2, and this is 10 to the 3, so like 100, 1000, and so on. So in a logarithmic scale. So maybe if I try to plot it, this isothermal diagram, maybe it would be somewhere here. I don't know. Yeah, so it's gonna start, usually the graph would be like this. So it's gonna increase, it's quite fast around here, and then it's gonna have a steady, and after that it will finish again. Okay, so around this one is called the nucleation phase, this one is the growth phase, and this one is the finish phase. Okay, so what we need to do in order to reduce the time, we need to do this reaction, the austenite to the perlite, at lower temperature than the eutectoid points. So instead we use it on 727 degrees Celsius, we make it a lower temperature, and it is called supercooling or undercooling. So if we make the phase transformation at lower temperature, what is the implication? The implication is, let's say, for example, at 675 degrees Celsius, it maybe start from maybe 10 or something, yeah, 11. And then if you increase that one up, it will finish into that one there, yeah, around something like that. Okay, I think you need to know how to read. Have you ever read logarithmic diagram? Hello, have you ever read logarithmic diagram? Have you ever read logarithmic diagram? I'm actually asking. Hello.
I think we have, ma'am.
Okay, you already have, yeah, in fluid mechanics, I think, yeah. Is it?
Yeah.
Yes, ma'am.
Okay, so but I'll just try to make it here. For example, if you want to read from here, you may want to, again, if I want to measure this, how to read, for example, from here, so I would start measure from 10 to uh, to to 100 here. So I want to measure these points. Let's say I just want to measure this point, so I will maybe make a line, my line, because I know the line there. So it is 1.57 centimeter, while this one is there, yeah, 4.2. So 157, 1.5, and 4.2. So here the scale is 1.5 divided by 4.2. So using the calculator, which is 1.5 divided by 4.2 is around about 0.36, yeah. So maybe it's around 0.36, but 0.36 is actually in the linear one. Okay, so then that would be, so the way you read it, it would be 10. Okay, so this is 10 power of 1 plus power of this one, so 1.36. Okay, so then what you can do, maybe you can open an Excel. Let's open the Excel, let's say, so, and then write 10 power of 1.36, and it's actually 22.9. So this one is actually 20, maybe what 23 seconds. Okay, so the time, this is actually start around 23 seconds. It is okay if you want to start at 0, maybe we have to move this line into here, so it's not really yeah, it's not really linear, so we're gonna start it here. Okay, and then for the final one, for example here, these points, I'm gonna measure it again, the scale. So from here, yeah, from the 10 to the 2 to this one, so 2.75 divided by this point, 4.35. So 2.75 divided by 4.35, and then I get 2.75 divided by 4.35, about 0.63, yeah, something like that. Okay, and here when I, so this point is actually 10 to the, this is 10 to the 2, yeah, 10 to the power of 2, and then plus this one. 2.63, which is, if I and then make the 10 to the 2.63 equal to 426 or 427. So this equal to 427 seconds. Okay, so it's actually if you do the transformation of eutectoid, for the eutectoid from the austenite to the perlite, if you do it at 675 degrees Celsius, it's actually just around about 400 seconds. Okay, 400 seconds, or maybe in a few minutes. Okay, however, if you cool it down lower to 600 degrees Celsius, then you just need time less than 10 seconds. Okay, so so you can see that how the temperature of the transformation is actually it will affect the time for the transformation. Okay. Okay, so I hope you should know how to use this scale, the logarithmic scale. Okay, so go back here. So for the transformation diagram of the Fe, the iron and carbon alloys, what we need to do is actually, so rather than we do it at a high temperature at 727 degrees Celsius, what can we do to make it faster is to do that with at a lower temperature. For example, if the green one is the 675 degrees Celsius, and then this one is at, or maybe at 650 degrees Celsius, and calculate it, or at 600. Just example. Maybe we can make it lower also. Yeah, it depends. Okay, so this is the effect of temperature of the eutectoid transformation. So it is the S curve. So the horizontal line is the time in a second. The vertical line is the percentage of perlite. Okay, so this point is when it is 0% of perlite, or where it is just 100% of austenite. Okay, in here at half of them, it is the 50% perlite has formed, and 50% remaining is still the austenite. Okay, and in here, when the time is finished, all of the austenite has been transformed into perlite. Okay, now okay, up to here, any questions? No? Okay, let's just move on to the next part. Maybe I can make it smaller, this one. I can just delete. Okay. Okay. Right. So now I'm gonna make from this one here. So back to here. Okay. So we have three important points. Okay. So we have the important one when 0%, and we have the important one, the point at 50%. Okay, and then we have also 100% at some temperature. Okay, so that is actually this transformation curve. It actually can be can be notified with these three essential points, when 0%, 50%, and 100%. So how if we transform them into another curve? Okay, so let's say this is at transformation temperature of 675 degrees Celsius, and then I put it into a time and also temperature diagram. Okay, so the horizontal one is still the same with this one. Yeah, is it still time for the horizontal axis, but for the temperature here we have scale in temperature. So let's say at transformation at 675, so over here, I plot the times exactly like on the top diagram into the red curve. The red curve is when the curve start begin the transformation, which is at around 0% per light. Okay, and the second one, the 50%, I make it into a dash curve, dash line and dash curve. Yeah, this is essential time. And then the last one is the green one, the green curve where it's transformation. Okay, so here you can see that around here the transformation occurs. This is from 0% austenite around this area. So the area, this area is actually all is austenite, but it's actually unstable. And then when you start to transform, it have 50%, and then it's become perlite 100%. Okay, and then let's do this one for this another transformation at different temperature. For example, at 600 degrees Celsius, okay, at 650 degrees Celsius, make again, and then we plot it, and it becomes like this one. Okay, and then we maybe make all the curve from the top one, from the 7 to 7, and this become this curve, and this curve is called time temperature transformation plot, because we know the information on time in second, we know also the temperature of the transformation, and we also know where is the phase are from. Yeah, where is the austenite and where is the perlite. Okay, so this is called the time temperature transformation plot for this system Fe and cementite at the eutectoid composition. Okay, then only for isothermal transformation, hanya proses transformasi isothermal. Okay, now and then here, if we start talking about from austenite become perlite. Okay, the perlite is actually alpha plus cementite. Okay, and we know actually this one is very brittle, and while perlite is quite ductile. Okay, so cementite is harder and more brittle compared to ferrite. So with the increasing carbon, the tensile strength, Brinell hardness number, and ductility toughness will decrease. Okay, and then this the thickness, yeah. So this one, the thickness ratio of ferrite and cementite layer is approximately 8.1. Okay, so remember the eutectoid curve, it looks like that, yeah. So you have the layer, okay. So if we consider this is the cementite, okay. So if this is the cementite, or this one, yeah, the purple one, and this one is the ferrite. Okay, and the thickness of ferrite and cementite layers is approximately 8 to 1. Okay, however, we will have a different microstructure if we cool it down at relatively high temperature, just below the eutectoid, and when it's actually cooled down up to around maybe 500 or 550 degrees Celsius around here, there would be a difference in phase transformation. Okay, at around here, when we have when we do the transformation around 700 degrees Celsius, we will have a thick layer of alpha ferrite. Okay, so at temperature just below eutectoid, a relatively thick layers for both alpha ferrite and cementite phase can be produced. Why? Because around this time or around this temperature, the diffusion of solid is still quite fast, and then so the carbon can diffuse, and they can diffuse and then make a thick Fe3C. Okay, however, at a lower temperature around here, the decreasing temperature, the carbon diffusion decrease and the layer become thinner. And the thin layer structure will be formed, we call fine perlite. Okay, on here is called coarse perlite. So if we look at here, around here, so if for example we do the isothermal transformation, let's say we have from maybe from 750 degrees Celsius, and then we cool it down very fast, but up to let's say 620 degrees Celsius, and then we hold the temperature. Also, the austenite can have a transformation with the increasing time. It will have the ferrite and cementite, but in here you're gonna end up with coarse perlite, and over here you're gonna end up with fine perlite. Okay, now so I think I have the one here in the book, so let me share the book as well. So let me share the book. Okay, so so this is a typical photomicrograph of the coarse perlite, this one B, okay, and then this one B is for the fine perlite. Okay, if you look at the coarse perlite, you have a quite thick the layers for ferrite, okay, alpha. You have quite thick layer of alpha and smaller cementite, okay, and then your batas interface area, but luas batas fasa is actually you have some but not too much. Okay, the second one is the fine perlite. If you look at here, all of them are almost black. Okay, all the black actually it caused by the fine perlite, which is all the fine layers of cementite. Okay, so if you have fine cementite, then your area for the interface become higher. Okay, so the implication of fine perlite would be stronger compared to a coarse perlite, because fine perlite is actually they can hold the all of the load, yeah, and they can block the dislocation more. Okay, so that it is. So even we do the same transformation from austenite to perlite, if we do the phase transformation at different temperature, we will have different microstructure too, and then we'll also have different result for the properties. Okay, go back to here. Okay, any question about this? Okay, so then so now we will learn so now we have learned two microstructure. Okay, so the microstructure from the one that we learned from the phase transformation, the first one is coarse perlite, and the second one is a fine perlite. Okay, everyone, so if in here you have a coarse perlite, but over here you have fine perlite. Which one is stronger? Which one is harder? Fine perlite is stronger compared to coarse perlite, because you have more interface area, lebih banyak batas fasanya. Okay, just for example, I have maybe cheese, yeah, or maybe or maybe tempe, let's say, yeah. Okay, if I can make this thick, okay, or if I can make this stick, maybe if I can make this stick, maybe only 1, 2, 3, 4, maybe only 4 pieces. So if you calculate uh, the interface area, luas batas fasa antar area, maybe only 4 multiply with the volume, with the surface area, 4 kali luas permukaan. Okay. However, if I have this tempe, for example, yeah, this tempe, and then I slice it really fine, really slice, maybe I can get instead of 5 instead of 20. So if you think about the area, the surface area, and then multiply with the how many those layers that you have, you will end up with a higher area, which is higher area. To block the dislocation means the material is stronger, and the material will resist plastic deformation. Okay, so with decreasing temperature, the diffusion increase and the rate will become progressively thinner. Okay, looks like I need to bring a drink. Just a moment, yeah, just wait for a minute. Okay, let's continue. Okay, so this one is strictly for eutectoid composition. Okay, because it only shows the transformation from austenite into perlite. Okay, now the question is, how if we have alloys paduan which the composition is not equal to the eutectoid composition? For example, we have 113% of a carbon, 1.13% of carbon, so it is a hypereutectoid. Yeah, remember? So in hypereutectoid, I still remember that we end up with Fe3 proeutectoid, and then after that we can get the perlite. Okay, so what do you have is actually, if you look at over here, this is would be the eutectoid temperature. Here you will have some curve, but in this area you will have austenite and also the cementite. Okay, so the cementite will first occur because it's a pro-eutectoid cementite here. Okay, and after that, from here, then if we cool it down, if we hold the temperature, then all the remaining austenite will become perlite. Okay, so if I can draw, let's say I started with this temperature 750, and I just quench them until 50 degrees Celsius. After this, so when we wait and then we hold it, so here after 1 second the transformation began and the cementite will form. Okay, karena dia sudah lewat jenuh. Okay, because it's oversaturated, then and the cementite will will appear. Okay, this one because the proeutectoid. Okay, until we have this one full of the austenite, the remaining austenite. And after that, the remaining, after about maybe 2 or 3 seconds, the austenite will start to transform, become the perlite. Okay, so that is the temperature. Okay, so would be the strategic for processing. So I would like to ask you in the exam, for example, so describe the process condition to obtain, let's say, hyper-eutectoid steel if I cool down into isothermal temperature of 650 degrees Celsius. Okay, so then you can say that, okay, so this should be quenched up to from maybe 750 degrees Celsius to 6 degrees Celsius, and then hold it for, yeah, maybe hold it to 100 degrees Celsius and 100 seconds. So to ensure all of the austenite here has transformed into perlite. Okay, so here, so the complete transformation, we will have perlite and also the cementite proeutectoid, similar with the previous one that on Monday I have or yesterday I have shown you. Okay, so this is the picture. I have the picture as well. So this one is the coarse perlite. This is the coarse perlite, and this one is the fine perlite. And you have the interface area for that one. Yeah. Okay. Now, a good question. Because this is not an equilibrium process. You actually end up with some of the microstructure, but that is not appeared in the phase diagram. Okay, what is called binite in here. So it's actually, if we cooled it fast enough to this temperature, yeah, rather than I cooled down not to maybe not to 650, but I want to cool down to 400 in a second, very fast, and then I hold it at 400 degrees Celsius and then just wait it for some time. What happened is the microstructure that resulted from the transformation is not perlite but binite. Okay, the binite here, this is the binite. And if we cool it down very fast up to 200 or 100 something, it will have will form, which is called martensite. Okay, so in the next slides we will learn each of all the microstructure. Okay, so what is binite? So binite is when we let's say if we like this, yeah, the 100% binite. If you look at in this example, okay, so if you cool down very fast and then you hold up, for example, 350, and then you hold that temperature for 10 to the 4 second or 10,000 second, what you end up is another microstructure which is called a binite. Okay, so what is binite? So we can look at here. So the binite is actually one of the microstructure from the transformation of austenite to like a perlite, but instead of it being layers between alpha and the cementite particles, so maybe I can draw if you know that in, let's say, the microstructure of ferrite, it looks like this one, right? It's like layers. So this is ferrite. Okay. However, in a binite, it have a different microstructure where if you have, this is the grain boundary, for example, it looks like just some plates, topi ringan, yeah, if you cross section, and the plate is actually a discontinuous. It's not continuous. So this is the Fa3C, and the matrix atau dasarnya ya is this alpha. Okay, So it is based on a matrix alpha and a particle of cementite, and then it looks like needles, jarum, or plates, so piringan. Okay, and it's very fine, sangat halus, only can be seen on a microscope electron, and it only happens on the eutectoid composition. Okay, and the transformation of austenite to bainite is around 250 degrees Celsius to 540 degrees Celsius. Okay, and then so here, if you look at over here, it is you can see this plates on here. It's not continuous. Here it's not continuous, and then up to here, and then here like that. Okay, so it looks like that. Okay, so the good thing about bainite, so the Fa3C needle and a plate, it act as like it act like to make the bainite stronger. Okay, so it's like adding the border or the you know the how to reduce the plastic deformation. Okay, it's going to act as a very strong material. Okay, however, alpha, yeah, the matrix is act as matrix is act as it can be used for slipping. Okay, so if we have some load, for example, here we have load like that, it can maybe sometimes go to here. Okay, it can sometimes go to here and then here and then here, so it still can be have a plastic deformation, lebih lunak, ya, lebih ductile. Okay, rather than here, if you have a load, it will be stuck all in the cementite there, yeah, because it is a very continuous layer, but in here the cementite is not continuous. Okay, so here the bainite, when it happens competitively with austenite. Transformasi austenite ke perlite sama dengan dan austenite to bainite, and if we want to make maybe, for example, from bainite to perlite, we want to make it again, we have to heat it up again up to austenite. Okay, because austenite is not stable. Okay, so because the bainite has fine particles with Ff3C, so it is gonna be stronger, akan lebih kuat. Okay, and also and with the alpha matrix, which is act for slipping, and then they can absorb energy, they can bend, yeah, they can have a plastic deformation, it will become ductile. Okay, so bainitic steel, baja bainitic steel is strong and ductile. Okay, so that is another phase transformation. Okay, so here I can show you that we have the first one is coarse perlite, the second one is fine perlite, and the third one is a bainite. Yeah, so if you go back here, so the third microstructure is called bainite. Okay, now the fourth one of the bainite, so we can have a look on the next slide. We also learn called spheroidite. Okay, the second one, the fourth one is called spheroidite. So if we have a steel which is perlitic, like that, so perlite, or bainitic, okay, and then if we heat it up with quite high temperature, for example 700 degrees Celsius, quite a long time, what happen is all of these plates, all of those layers, they will shorten up. Dia akan mengumpul. All the Fe3C, the cementite, yeah, this one of a cementite. All of the cementite will reduce the area and it's become a spherical one. Okay, so here baja yang dengan struktur perlitik atau bainitik dipanaskan hingga temperatur tepat di bawah eutectoid dibiarkan pada waktu yang panjang, dia akan punya struktur mikro baru spheroiditic. Okay, so all of this iron or the cementite is actually they will reduce the interface area, akan mengurangi batas fasanya, and it become like that one, maybe like that. Yeah, and then where all the nodules, all the sphere is called the cementite, and the matrix is still the alpha. Okay, so you can see here over here that here, yeah, you can see that all the nodules here is the Fe3C. Okay, yeah, this one also, and the matrix is actually the alpha. The Fe3C always act as the border, yeah, so to make it strong, but it's not as strong as a perlite of bainitic steel, because then we see that the area has been reduced significantly. Okay, and alpha will act as a matrix, and it also can slip. Yeah, it can slip, so it can bend, so it is ductile and toughness. Okay, so then the spheroidite steel, baja spheroidite, is all of the alloys that is the most softest alloy compared to the previous one, and very less stronger, but it is have very high ductility and also very high toughness compared to perlite. Why? Because the volume, the interface area per volume unit of the spheroiditic become very reduced. Okay, because those area it has been reduced into a sphere, and then the matrix is actually can act as a slipping, and then can reduce the crack propagation. Okay, so it is very ductile. So sometimes when we have a bainitic steel and perlite steel, if we want to increase the toughness and the ductility, what we need to do is we need to put it back into a high temperature, but still below the austenitic region, about 700 degrees Celsius, and then wait for quite long time. So it allows to the diffusion of all the carbons and the cementite to make a new shape, which is a sphere. Okay. Okay, so that is the number 4 about the spheroidite. Okay, and the last one is the martensite. Or maybe not the last one, yeah. I think there should be one more. Yeah, later. Okay, so this is martensite. If we look at the graph here, the martensite will happen at a very low temperature. So if we cool it down, this austenitic steel at around about 200 here, around here, and then we cool it down like that, just before they need to transform, lower than this curve, we will have 100% of martensite. Okay, so 100% of martensite, and then what is martensite? So we can see that this is the martensite. Okay, so the martensite is it is again similar to the bainite, but it is it's actually a mixture of needles. Okay, the needles and then some plates. Okay, so this is all the martensite. And then it is very strong. It is the strongest alloys compared to the perlite and the bainite something. Okay, and then if you look at here, the if we quench them pendinginan cepat, yeah, quenching from the austenite from temperature of room temperature, from the high temperature to the room temperature, the microstructure we know is martensite, is a non-equilibrium phase, and then it is actually gonna change into BCT martensite. So from FCC austenite, maybe like that. Okay, so like FCC, it will become body center tetragonal. So it become like higher there, body center tetragonal. Okay, and then it's called a thermal transformation, and then the still with the microstructure of martensite is the strongest, the hardest, and very, very brittle. Okay, and then the increasing martensite will increase until this concentration. Okay, so everyone, you can see that we have learned up to now there is 5 of the microstructure, and the last one is I think there's another one. Okay, I think so I think I can sum up for now here that we have learned 5 transformation, phase transformation. The first one is perlite. Yeah, there are coarse perlite and fine perlite. Okay, and then we know there's also bainite, and then we also know there's, if we heat treat the bainite at 700 degrees Celsius and then wait for a long time, it's gonna be spheroidite. And the last one, if we quench the austenite to the room temperature, is called martensite. Okay, just to sum up a little bit, which microstructure which is the strongest, of the of all, or the hardest of all?
Martensite, ma'am.
Oh yeah, martensite. Okay, which one is the most ductile compared to the others? Or the lowest, or the less stronger? Yeah, the which one? It can be bainite, yeah, or it's actually spheroidite, yeah, because bainite is ductile, but it would be more ductile again with spheroidite, because if you see the spheroidite here, they have quite longer matrix, alpha matrix. Okay, so the spheroidite, still by the spheroidite is the alloys that is the most soft, the softest alloy and the very weak alloy, but it is the most ductility of all, yeah, compared to the alloys. Okay, so before this, any questions? Not yet. Okay, so later on maybe we can use some of the example question, let's say usually from this example. For example, can you describe how the process to get 100% martensite, for example? So if you want to have a martensite, we can see this graph number B over here. So you have to cool it down up to 50 degrees Celsius, and then maybe just hold up to 100 seconds and then quench down again to room temperature. Then you will get 100% martensite. Okay, and if you want to have 50% perlite and 50% bainite, that's also possible. What you need to do is you need to cool it down to maybe 50 degrees Celsius, but hold it only up to the blue dash over here. Okay, after that you have to cool it down again to 400 degrees Celsius. So all the remaining austenite here will be transformed into bainite in no time. Okay, in some time around here, up to 1000 seconds. Okay, so here, you can see also this one from the example in the book. Okay, here. So what happens? So the one that we see is actually for the eutectoid alloys. Okay, so eutectoid only carbon and also the iron. Okay, what happened for AISI 4340, for example? I think this one they have some alloys unsur pemadu, yeah. For example, chrome, nickel, molybdenum, and so on. So they will end up with their mapping. Okay, so in here, in their mapping, they have there are two nodes over here, and then if you look at the time, in the previous one, if I can go back here, the transformation is happen very fast, like less than 1 second it has started. Okay, but however, if we add some alloys, the transformation actually will start quite longer compared to the previous one, like around maybe 200 or 300 seconds. So it takes for us some time in the process in the industry to prepare everything right. Okay, so because sometimes it's very hard for us to get a process that in 1 second they have to change, okay, maybe the temperature and so on. So if we have if we add some alloys here, it can the nose of here it actually bergeser ke T lebih tinggi, ya. So this one the nose of the transformation diagram, the isothermal paralytic and the proeutectoid will shift into the high time, okay, higher time. So it can make some adjustment for the operational services. Okay, and this one also the temperature, the transformation of magnetic also like this, and also the martensitic also the increasing would be higher. Okay, so I think it is going to be useful for us to see the transformation magnetic like this one. Okay, and you see that later on for materials engineers there would be a number of graphics like this, the nomograms like this, and then it would be specified for each type of alloys. All right. So that is the isothermal transformations. Okay, so the key is isothermal transformation. Okay. So the way the isothermal transformation is, you have to cool it down to some temperature and then hold it up for some time and then cool it down to the quench again to the room temperature. Okay, so like this, you bring the temperature quench into some temperature and then hold it up and then cool it down. Okay, it can be happening, it can be applied in the industry, but still it's not really easy. Yeah? It is quite tricky how to control the temperature. Yeah, because so later on next year at semester 6 you will learn about process controls, and it's very hard if we have to control like this, when we have to sudden a drop of quenching and then try to hold it up, the temperature can't decrease. Okay, and then yeah, like that. Okay, so the next things that I would like to explain to you, which is would be much more applied in the industry, is called pendinginan kontinu or continuous cooling transformation. Okay, so the next one I would like to see is continuous cooling transformation. Okay, so this one. Okay, so yeah, so it's also written here. So the heat treatment of isothermal is not practical, which is we have to quench and then hold it for some time and then cool it down. So in the industry, the one that we often see is actually the continuous cooling atau perlakuan panas pada pendinginan kontinu. So continuous cooling transformation. Okay, so what is the continuous cooling transformation? I'll just give an example like this. Okay, so the continuous cooling transformation, it would be looks like this one. So for example, here, so in a continuous cooling transformation, instead if the isothermal transformation is all dash curve, this one is the one here is the continuous cooling. So the way it cools is actually from here. So this part is actually shows you pendinginan perlahan. Okay, so like the cooling, the continuous cooling, for example, how many degrees Celsius per minute of the cooling. Okay, so here, for example, so this one, for example, the blue one is for slow cooling curve or full annealing, and then we will have a coarse perlite. Okay, over here. So here, the slow cooling curve, full annealing, while over here is called moderately rapid cooling curve, which is normalizing to get a fine perlite. Or if you want, you can add some different, maybe higher rates, yeah, like this. So it's actually to get the rates, yeah, to get the cooling rate. To get the cooling rate is actually as it would be as simple as delta T divided by delta time. Okay, but however, the time is in logarithmic. So you have to be careful that one. Okay, so be careful, the area would be on logarithmic. Okay, so that is the cooling rate. So the slow cooling, for example, like I said before, one of the example of slow cooling, if you have if you heat it up the alloys at high temperature, and then you turn off the source of heat. Okay, you turn off your fire, you turn off your combustion, but then you just still put the your metal inside the furnace, and then let the furnace cool slowly until room temperature. So it is quite slow cooling. Okay, in moderate cooling, for example, if we have metal and then it is spread it out by the what's called the oil, okay, some oil, or if it is a high rapid cooling, a very rapid cooling, maybe we need to, you know, spray it with a lot of water. Okay, a lot of water to make it cool down. Okay, so maybe I think I can show I think the video, yeah. Maybe wait before, let me check if I still have the video about the transformation, the cooling transformation. I think we saw the video for a few weeks ago about the steel processing. Wait. Oh yeah, this one, yeah. So let me close them and share again the screen. So I think around, oh yeah, so okay, this one. So let's say when we have this one from after we got the steel, and then we make it into this one is slab, yeah. So you can imagine that it is gonna be very hot, yeah. For example, it's still solid but still like burnt, membara, yeah. It's going around maybe 800 degrees Celsius, and then it's cool it down, and then when you cool it down, sometimes we add in all these sides is we add can be added by some water or also oils, yeah, just to heat it up or just cool it down. Okay, so maybe we can watch from here. Okay, just want to show the how the process works.
Create purified molten steel. At this point, the temperature and substance composition of the molten steel is precisely adjusted according to the customer's various demands. Pouring the molten steel into molds and cooling it into solid steel creates a semi-finished material
Yeah, so this is the
ready to be
cooling.
made into finished steel products. The solid steel is categorized depending on its shape. Slabs are wide and flat. Blooms are rectangular bars. And billets are thinner square bars. The final stage of producing steel is the continuous casting process where steel is forged into various steel products.
Oh,
When a
this
slab
hot
is
steel.
heated above 1,100 degrees Celsius and passed between rollers, it turns into a thin and long steel sheet. This hot rolled product is used widely as construction materials and pipes in various industries.
Okay, so if you can see that one, all the hot steel, you can see some steam over there. So where is it?
Products.
So let me wait.
When a slab is heated above 1,100 degrees Celsius and passed between rollers.
Yeah. So this one is actually the water. Okay, so it is with the continuous cooling transformation, we want to transform and change the microstructure by adding some water. So the water will absorb the heat and then it will gonna be cooled down. Okay, so that's just one example. In some other places they put oil as well, just to quench with oil, so it is moderately cooling. Okay, yeah, we have seen this picture before, this video before, so maybe we can close it. Yeah, so maybe just watch a little bit.
Turns into a thin and long steel sheet. This hot rolled product is used widely as construction materials and pipes in various industries. Cold rolled products, which are created by making hot rolled products thinner at room temperature, are used in general appliances, barrels, and automobile frames. Coated steel, which is created by coating cold rolled.
Yeah, that one. Yeah, so you can see that one side how to get the continuous cooling transformation. Okay, I think I go back to here. Okay, so this one is the continuous cooling transformation when we see the cooling rate over here. Okay, so you can see here is, for example, between austenite and perlite. So in austenite and perlite transformation, we see that there is a critical cooling rate. Okay, so this one is called the critical cooling rate. For example, this is 35 degrees Celsius. If it is slower than 35 degrees Celsius, then you will have perlite. Okay, let's say I cool the steel with, for example, 50 degree Celsius per second. Maybe only 20 degrees less than that. Yeah, less than that. 20 degrees Celsius per second. Then you will end up with perlite. Okay, if you have a cooling rate between 35 and 140 degrees Celsius, you will end up with martensite and perlite. And if it is higher than 140 degrees Celsius per second, the critical cooling rate, you will get martensite. Okay, it should be noted that in this continuous cooling transformation, we don't have bainite. Yeah, we don't have bainite here. Why? Because all of them have been transformed into perlite. Okay, so we can't have bainite in the continuous cooling transformation. Only perlite, mixture of martensite and perlite, or martensite. Okay, so let's continue. Okay, so what happened if this one? So what happened if we have alloys? Okay, so if we have alloys here, it is become sometimes we have a bainite. So that, for example, we have some alloys, chrome, nickel, molybdenum, manganese, and silicon. It actually will decrease the cooling rate. Okay, so here the cooling rate, it can reduce significantly. For example, in the previous one, from here you have 140 degrees Celsius should be larger than 140 degrees Celsius to get the martensite. However, in here you only have to have more than 8.3 degrees Celsius per second. So it allows us for the process to process them, and if you want to make maybe the wanted the alloys that we want. So it's easier to make martensite, for example. Martensite is very useful because it's very strong, but however it is very brittle. So we have to make sure that the application should comply with the properties. Okay, so here so the alloys is actually all the nodes of the pearlite and bainite, so they will also bainite, and again it will shift into high into a longer time. Okay, menurunkan laju pendinginan kritik. Okay, so then you will have some time to reduce the cooling rate. Okay, so to get the pearlite you should be very slowly, like 0.0006 degrees Celsius per second, and then if like in a moderate one you can get the mixture of martensite and bainite, or martensite ferrite and bainite. Okay, so it depends on that one. Okay, so to sum up, it's actually between the continuous cooling transformation or the isothermal transformation, by designing the process on the graph, on the diagram, you're gonna end up with the microstructure. Okay, and those microstructure will also have implication on how about the properties of the metals. So let's say we see that the mechanical properties of the alloys, iron and carbon only. Here, for example, we have this is the 0.76, yeah, which is for the eutectoid. Okay, here. Around here is pearlite and ferrite, which is hypoeutectoid, and over here is the pearlite plus cementite, or the hypereutectoid. Hypereutectoid steel. Okay, so here you can see that the strength. Okay, the strength is for example here, and then the brittle hardness as well. And then of course, with the increasing of carbon, the hypoeutectoid steel would be much stronger compared to the hypoeutectoid steel. Yeah, because with the increasing carbon, of course, because cementite or the carbon is brittle and stronger compared to the ferrite. Okay, so if you have pearlite and ferrite, it is ranging from here around yield strength and tensile strength, maybe about here around 400 megapascal, but it can increase up to almost more than 1,000, yeah, almost 2.5 times if you increase the composition of carbon. Okay, so it is very much different. For example, this one hypoeutectoid steel is for gears from machineries, yeah, very strong tools. But in here, for example, maybe for hypoeutectoid steel, it is good for appliances, for the body of electronic casing, or only for a pipe for maybe with lower schedule number, something, yeah, with for only for atmospheric pressure. Yeah, that would be you can see the difference between of this one. Okay, and then but again, if you look at the ductility and the impact energy, okay, the impact energy tells you about toughness. Okay, this is using ISOD impact energy, and then the ductility in the percentage of the ductility in the percentage of reduction of area, percent of area reduction, or the percentage of elongation. You can see that here the pearlite and ferrite has a high impact energy and just decrease significantly as you increase the percentage of carbon. Okay, so again, it is based on based on how we select the material, how much impact energy do we want, how much the strength that we want, in order to see what is the composition that we want. Is it hypoeutectoid or is it hypoeutectoid, and then so which part. Okay, Okay, so and then if we compare it, okay, so at the similar composition, let's say here, okay, it can be the Brinell hardness number around, which would be the measure for hardness. Okay, so the fine perlite has much harder compared to coarse perlite, and the lower one is the spherodite. Okay, so it's similar with our suspicion before my explanation before, because in spherodite we have nodules or sphere of those Fa3C, while in the fine perlite you have a very thin layers of cementite that act as a border for plastic deformation. Okay, but however, again, if you look at the ductility, you can see here it also, the spherodite has a very high of ductility in the percentage of reduction area, and then here the coarse perlite slightly higher compared to the fine perlite. Okay, right, so then and this one is the transformation temperature of the bainite and perlite. So how we ensure that how can we know that the one that we want is actually perlite microstructure or bainite microstructure is actually, so perlite started from 700 up to around 540 degrees Celsius, while bainite is actually from 540 up to around room temperature on here. And this also tells you about the Brinell hardness number of bainite and perlite. Okay, so bainite is actually stronger than perlite, yeah, if you see, or harder than perlite, because bainite we have some more needles of those cementite, so it can act as a border again for plastic deformation. And here in this case we can see the composition versus again the hardness again. Okay, even in a Brinell hardness number, of if you want to convert it into Rockwell hardness number, it is the martensite. So the martensite is very hard. And then this is a tempered martensite. The tempered martensite means the martensite which is we heat it up again in some temperature just to lower the what's called the needles, yeah, the needles, to increase the ductility again. And then this one is fine perlite. Okay, so maybe if we want to add spherodite, maybe around here or something. Okay, so you at least you should know the ideas and the logics about which one is the stronger, which one is the next stronger, and so on. Okay, so the last one is tempered martensite. The tempered martensite looks like this. So I think this one I can explain it in this graph. So if we have martensite, which is have a lot of needle like that, so this is the martensite, and then we do the tempering. All of those needle, again similar with the bainite to transform into spherodite, those needle will reduce the area of the interface, akan memperkecil luas batas fasa. Okay, so if we look at here, so with the temperature of tempering, with some diffusion, then the cementite will it actually will rearrange themselves to make it a little bit sphere or ellipse. Okay, and then it will increase the ductility of them. Okay, so the tempering, what is called tempering, it is the heating. So once we have the martensite, and the martensite is very brittle, and it's very brittle, so it's not useful, tidak berguna. So what we need to do, usually we like tempering the martensite. So we heat it up again in some temperature between 250 to 650 degrees Celsius for some time. So they again can rearrange up to this type of microstructure. Okay, so here we have the matrix, yeah. So we have the alpha as a matrix. So the continuous means ductility is increasing. So which is would be increasing ductility. And then the cementite, the Fa3C, will act as the the stronger one, as the border for the plastic deformation. Okay, so it looks like this. So we also have the graph of the temperature for the time of tempering of 1 hour, 1 jam. So if we make the tempering around here, the reduction in area up to here, and the yield strength will be also decreased. Okay, so if we do the tempering at a quite high temperature, the tensile strength will decrease, yeah, from the previous one, but then we will have some area reduction, some ductility. Okay, so again, when we want to do the tempering martensite, sometimes we have to check the objective of the tempered martensite, which one that we want, and then we can see the Rockwell hardness and so on. Yeah, so for example here, this is the time and then how long, yeah, it actually will comply, which actually will be connected with how much Rockwell hardness number or the Brinell hardness number of those martensite. Okay, so here to sum up is actually we also have some tempered embrittlement. So all the tempering is actually how to increase. Yeah, so if we have a tempering, sometimes it's we change the composition, or with quenching, so it would be increasing of the toughness. Okay, so because so sometimes the tempering it will have some brittle crack something, so we need to change the composition and then change the tempering. Okay, so to sum up, it's actually here maybe I can make it bigger. Here, yeah, I think this one is the one that you the one that you need to know. Maybe make it bigger in one slide. Okay, so okay, so it's actually when here you can see that so we know all of them. Okay, so all the microstructure. The first one we know the austenite, which is this one is unstable. Wait, close it down. Unstable. So this one is unstable. Okay. Unstable. Okay. With the continuous cooling transformation, if it is slow cooling, you will have perlite or pro-eutectoid phase. If it is not eutectoid still, okay. So you have perlite. If you have a moderate cooling, you will have bainite. And again, if the bainite, if you do the heat it up for some time, you can end up with spheroidite. Okay. Or for the rapid quench, here you have martensite, and then you can reheat it again to have the tempered martensite. Okay, so that's all the topics for phase transformation. So by changing the cooling transformation, the cooling rate, okay, so we can end up with different microstructure. Okay, so in here some exercise. Okay, so for example here, an example or sample of the exam. So write the steps for the isothermal cooling to get the microstructure. For example, 50% of fine perlite, 50% of bainite, or 100% martensite, or something like that. Thank you. Okay, and then this is actually, if you look at here, if you want to do it exercise at home, you can see that it is actually, it is Fe with 0.45 percent of carbon. So it is hypoeutectoid or hypereutectoid. Hypoeutectoid or hypereutectoid. So which one is right? Hypoeutectoid or hypereutectoid? Who want to try to answer? With the eutectoid composition, 0.76%, is it lower than 0.67% or higher than 0.67%?
Higher now?
Yeah?
It's higher than 60%.
Higher or lower? This one compared to the eutectoid, higher or lower?
Lower, lower.
Lower. So if lower, then it is a hypo. Okay? Because it is a hypoeutectoid still, when you look at the microstructure, you will end up with a proeutectoid ferrite or alpha plus perlite. Okay, that's why in this graph, when you cool it down, the transformation diagram here, from austenite, you end up with A plus F, this one. Yeah, so A plus F, so that would be a region where you have austenite and you have ferrite. Okay, so now the ferrite is stable. Sudah jadi ya, ferrite stable, while the remaining is austenite, and then the next one, austenite, will transform into perlite. Okay, so that one. Okay, so here next question. Okay, next question, for example, calculate the composition and the microstructure needed if we want to have 160 Brinell hardness number and the minimum of 52 of reduction area. Okay, so here is actually what we can see. We can find the ductility. So your task is actually find in the book or find in the exam, for example, about all the graph related to this one, and then first you want to see the ductility, ya, keulutan minimum, the ductility, the percentage of ductility. Okay, it should be minimum 52% reduction area. So find the ductility with a reduction area about 52, about this, and then look at that one. So that it would be your composition. Yeah, it is fine perlite or coarse perlite, but you can't get this peridot. Okay, and then look at here that this is the hardness. Okay, kekerasan minimum 160 hardness Brinell. Okay, so then you need to see the composition of here. Okay, yeah, it's either fine perlite with this composition or coarse perlite with this composition, and then peridot with this composition. Okay, let's say we have fine perlite with this composition, For example, 0.25, 0.26, let's say, yeah, it's a very similar, and then put the 0.26 over here. Okay, and then draw the line for fine perlite, and it's actually, it becomes 52, which is similar. Okay, so then if you want to find the composition needed, so you need to have the composition of 0.26 weight% of carbon with the microstructure is the fine perlite. Okay, so you can try it by yourself at home. Of course, not assignments, but try that as a practice before the exam. The composition and the structure the microstructure, I mean, for the alloys, when you have the mineral hardness number and the minimum of the ductility of something, you need to check in both graph and then health, and then from that one you will find the answer. Okay. All right, I think that's all for today. So before we close, if you have any questions, so I would like to welcome you. Okay.
Ma'am,
Yes.
I would like to ask small question, ma'am. For our exam, is that already like a schedule, ma'am?
Okay, the exam would be on week 8, everyone. Okay, so from this semester, the Directorate Pendidikan said that the exam should be held on the campus, on site, Luring. Okay, but with this condition, we don't know. But all the programs, the chemical engineering program has asked the lecturers to keep all of the exam on the week 8. Okay, but be careful. So that means on your week 8, which is on the next 2 weeks, you will have all the exam that one there. Okay, so how many courses that you take this semester? 4, 5?
For the compulsory ones, around like 5, I think, ma'am.
5, yeah, 5, one for the compulsory one and one for the maybe for the elective. Okay, so that is time management, yeah, for you. So in the next 2 weeks there would be 5, maybe 5 courses. Well, all would be so there would be no lecture, and all of them should be located for the exam. Okay. However, it would be on site or still online mode. We still wait for the the development of this COVID pandemic. Okay, right. So next week, or we will maybe I will continue with the last topics about the application and processing. Hopefully it's not that much. Maybe we can have a 1 hour because you can read it actually. So next Wednesday we can start to have a tutorials or latihan soal ya, and then to prepare the exam. So during the exam you should be able, you should have the hands-on to read the book, the Callister book, or you open all your slides, yeah, and then check the not to check the recording, but you know where to see this type of question. All right, any other question, please? All right. Okay then. Okay, so I think I'll see you again next Tuesday. And then don't forget there's assignment about the phase diagram. And then if you have any question or something, and then we'll need to arrange the tutorials as well. So who is the class coordinator? Still Azra, maybe? Yeah. Okay.
Yes.
Let's say Azra is the coordinator. Okay, so later on me and the teaching team will maybe arrange the tutorials and with the assistant as well. Once I know the information, I will let you know. Okay, everyone, thank you very much, and see you again next week. Bye bye.
Thank you very much, ma'am.